Okay? Not working? Don't have another calculator? Alright.
You typed it. You typed it in. Nice. So bad.
Alright.
Oh, that was you.
I think we're gonna do a lab.
Oh.
Why don't we have all things? Where's the one that you screened?
No, we'll do lab
Everyone
Wednesday.
has that
Lab
much
Wednesday. Lab Wednesday.
No, it's 0.85 times 1.3.
That's cool.
Alright, we have our next gas law. So you're gonna want to get to your gas law table.
There we go.
The gas law table that you have to fill out and memorize. Did you hear that, Maddie?
Oh, I get it.
May not have been
Like,
here
you
when I
can't do it
said
that way as long
I
as.
sold it. It's suitcase, that's why.
So this thing,
That's why.
this exact thing will be on your test, like blank. You'll have to fill it in.
And names and everything.
And names and everything.
Yeah, see.
Alright? Now you're gonna see some similarities between most of these equations.
Great.
All these equations are going to have similar variables. Okay? Well, yes and no, depends.
Charlie.
Okay? So Mr. Charles, so just like Boyle studied how pressure and volume related to each other when you kept the other variables constant, Charles studied how volume and temperature were related when he studied and held all the other things constant. No, good question. So what I want you to do is for the law, I want you to put the name. So Charles is what you would put in for the name, and you're going to put in the second equation. Okay, remember, this is the equation I want you to put in, and this is where the equation comes from, which I believe I showed you how that worked on Friday with Boyle's law, right? And I can show you again with Charles' law, just in case you.
Did we do this in physical science?
Yep.
Shoot.
And then, any idea what your constants are? Okay, pressure is 1. It doesn't say up here what the other one is, but moles. Okay, it's kind of assumed that in all these moles are constant because you could imagine that if you had more moles or more particles, wouldn't that affect all of them? More particles would mean you have to have more volume, which would change the pressure, which could change the temperature. And so we're going to see how eventually all of these guys are going to fit into one equation, which is known as the ideal gas law, which none of you will forget. I promise you.
Do they teach double rounding, like some places?
Why would you do that?
Like,
Let's get a number that was like 99.444444444. Wait, is that PV equals nRT? Round up, round up, round up.
that's why you'll never forget it. That's coming. All right? So here we go. B over T equals K. Where this comes from is that what Charles noticed is there was a direct relationship between these two variables when all the others were held constant. What does direct relationship mean?
They both go up inverse or not inverse.
The opposite of inverse. Okay, so what is the opposite of inverse?
They both go together.
They either both go up or they both go
down.
Okay, so let me show you. Let's say the volume was 10 and the temperature was 5. What would that give you for a K?
That'd be 2.
9.
Okay? So let's say I increase the volume to 20. The temperature, since it is also directly related, will go up proportionally to 10, still giving you 2, and I can continue to do this. And since it always gives us a constant, we can take these two things and set them equal to each other, because the constant will always be the same. And that's why this is the usable equation, and this is where it came from. So, equation, or I think I got a visual here. Let's in our mind theorize this. Okay, remember what has to be constant.
Pressure and
Okay. Pressure's constant. All right?
So our next law is gonna be volume constant, pressure, temperature.
Yep. Mr. Gamusay. Okay? So as you can see by this visual, it appears that the temperature is going up, so it's heating. Okay? So let's talk about, in theory here, conceptually what's going on. This is important because we are doing a lot of math this chapter, but there was a whole load of conceptual stuff here. Could I ask you on an essay question, explain why, when the temperature goes up, the volume increases?
I hope you don't.
Could you explain that? So listen carefully. Okay? First of all, do you know what temperature is?
Kind of.
The
Thermal energy.
average kinetic energy. What is kinetic energy related to?
Movement.
Movement, okay? So if you increase the temperature, you're going to increase their,
Movement.
okay, or their speed, yes.
Okay.
Okay? So they're moving faster. So if I took and I heated this up, that would mean these particles would move faster, right?
Right.
Which means they would, in theory, hit the walls of the container more often, correct? And with more force, because they're moving faster. What would that do to the pressure? That would increase the pressure, but we said the pressure has to stay what? Constant. So in order to keep the pressure constant, what has to change? The volume has to change. Does everybody understand that? In order to keep the pressure constant here, the volume is going to increase, because if you have more volume, even though you're moving faster, it's going to take more time to hit the container, and it's going to make the pressure equal out again. Okay? Same could be said if you decrease the temperature. You would decrease the volume to maintain that equal pressure, or that constant pressure. Now, this is something that you're going to need to put in your notes. The next things that come out of my mouth. Temperature must be in Kelvin.
Why is it not?
Why?
That's a scientific one.
Because Celsius goes in the negatives, which you can't do a nice linear relationship when you plop down into the negatives. And since this is a proportion, essentially what this is a proportion, which is very much related to linear relationships. Kelvin is perfectly linear, aka it goes all the way down to the coldest temperature at 0 Kelvin, right? And then it goes up proportionally to the highest temperature, which is, I don't know.
So temperature must be in Kelvin.
Yes, temperature must be in Kelvin. You will not get the correct answer because it isn't a linear relationship if you have it in Celsius. This is one of the main reasons why they even have the Kelvin scale. Because of the ease of math for us. So, let's look at this problem. We need to start labeling some variables. Okay, a sample of gas occupies 430 milliliters when it is at a temperature of 25 degrees Celsius. There's our first conditions. V1 is? T1 is? How do I convert that to Celsius? Celsius.
Plus
Kelvin. Plus 273.
115.
We're going to leave out 0.15.
Oh no.
I know. Not exact, but if we did everything exact in chemistry, it would take us infinitely longer. Okay? Then it says, oops, wait there, alright. What volume will it occupy? So that's V2 is what we're solving for.
What is speed?
Ah, why don't you look back in your notes, guys?
Oh. Standard temperature.
Mine does not say.
72 Fahrenheit.
72? Yeah.
207.
Ooh, where'd you find that? In the notes, right above Boyle's Law. Everybody turn back the page.
Oh, you're right.
Right above Boyle's Law, it tells you what STP is, or standard temperature and pressure. What is the standard temperature of that STP?
273.
You're going to need to know that, because if you don't know that, and this was a quiz question, would you be able to solve it?
No.
Wait, so complete 0 is standard temperature?
complete zero?
Oh, never mind.
It's equivalent to 0 degrees Celsius.
Complete zero. Zero Kelvin.
I don't know why I put 0. Yeah, that's in Celsius.
So 32 degrees Fahrenheit.
No. This is equivalent to 0 degrees Fahrenheit. Or no, sorry, yes. Sorry, Celsius. Yes, you're right. You're right. Okay. Sorry. I thought you were saying Celsius. Okay? So our equation now, the variables should tell you, I know you're probably like, well, we're doing Charles' law right now, but doesn't the variables tell you that this isn't Boyle's law?
Yeah. Boilies.
Okay? It's not pressure and volume, so it's not Boyle's law, it's Charles' law. What?
No, you just said you can tell it's not Boyle's law. It's like it's Boilies. I thought you said Charles.
What?
It's actually Charlie's.
Okay. Now, we're solving for V2. Okay, so I'm going to do this before I plug in the numbers. Why am I multiplying by T2? Stacked, right? Multiplying by T2 because T2 was on the bottom and you gotta do the opposite of it. Everyone should be good with that by now. Oh, stop it. Okay, then plug in and solve. Why don't you guys do that?
It's 390.
390? Do I have a second for that? Everybody else just gonna mooch off those two?
Good.
No.
I fucking love mooching.
Yeah. What are the units?
Milliliters and nice.
Okay, you should be plugging this in to clarify that you know you're doing the exact same thing, you're doing it correctly. Okay, if you just sit back and assume that's the correct answer, that doesn't mean you know how to do that. What did you do?
I got 393.
Oh,
Well, you got a round three.
Oh, so.
Yep. All right, I want you guys to do this problem.
Do units not matter as an actual?
Yeah, why?
Like before we were making our equations based off of units.
Well, like if these were in different units, like if one was in Celsius, one was in Kelvin, they
Oh,
would
so
both
just
need to be in Kelvin. Or
okay.
like if that was in milliliters and that was in liters, you have to get them to equal each other.
Oh, really?
Because this is just a proportion, as long as your units are equivalent, that's all that matters.
I do.
Gage, got an answer?
I'm thinking.
When you have an answer, raise your hand, I'll come check.
I got it.
Put your answer down there with the correct unit.
I got it.
Make sure you fill out your
I got it.
your chart, your gas law chart. That would be tragic if you didn't have that.
Go ahead.
What gas was- Is that right, Kramer?
Go ahead.
What gas
Is that what you did?
That one.
Yep.
Right in front of your face.
So I did.
Yep. Yep. Raise your hand if you got it done, so I can come check. I want to make sure you're doing it right.
I knew I could. I don't know if I got it right.
What are your units? You could be doing it right there.
It is.
Yep. That should have one more thing. That is 3.
Oh,
Who else?
I'll try it.
Got her?
I'll try it.
Yeah.
Like, what do you mean, like sig figs wise?
Yeah, which.
You would look at all three of them.
Yeah.
Yeah, all of them have 3 sig figs, so it should be around 8. I think they'll round to 8.
Ow.
Oh, shit, I forgot.
Did convert
What is your
Kelvin. There must be Calvin.
cows, monkeys?
I was thinking this entire
Sorry,
time.
didn't even do Calvin.
Hold on, we're
It's-
getting.
Okay, that is a very common mistake. If you don't switch it to Calvin, it's a big enough mistake that I'll count you 2 points off for a math problem.
Wow.
Okay.
Okay? So don't forget that. That's for temperature. Did everybody get 2.5 in? I didn't see everybody's, but is that good? Do you have any questions about whether they did something wrong? Okay. Mr. French guy here. Can you
That
say?
sounds like a gas law.
Okay? So now, as you can tell, you should be filling out your gas law chart.
Constant is gonna be.
Your gas law chart should be gas law 3.
Constant is gonna be volume
Volume.
and mold.
Volume and mold, yep.
It's crazy how like.
What was that? Well, it's not pressure because pressure's in here, so it can't be constant, so it has to be volume. Volume is the variable that's not in there. So your constants are volume and moles.
Why is it always mold?
Because we're gonna get to a law that has moles in it later. Because if you changed how many particles you had, that would change all of these. Okay? I'm not gonna go into the K, I think you guys are pretty good with that by now. Here's a visual, it's kinda hard to see. Good, yeah, real hard to see. What, okay, this, I think says 75 Kelvin, this says 150 Kelvin, this says 300 Kelvin. So what's happening from left to right?
Temperature goes up, pressure has
Temperature's
to go up.
increasing. Notice what didn't change.
Volume.
Okay, so what this is saying is in order to keep the volume constant, because we know that increased temperature is going to increase the volume from whose law? Whose law?
Charlie's. Charles.
Charles, right? V and T. When temperature goes up, what else goes up? Volume, okay? So in order to keep volume constant in this situation, we would have to exert more pressure to maintain a constant volume. And that's what Gay-Lussac discovered. Okay?
Why is his name like that?
He's French.
Like, why is there a
I don't know. Why?
Maybe he was adopted.
His parents
Maybe he
probably
didn't like just having his last name be gay. So he said,
So that probably didn't happen when he was alive.
probably.
And in French, that could mean something completely different.
Alright, let's do this particular guy. I'm gonna go through this one really quickly. I want to get to one other one.
Actually, that's a girl. Gender pronouns.
Molly.
Whatever. Okay? Before Molly. I can't even talk.
Molly?
Before Molly
Whoa.
began a car trip, she measured the air pressure in her car tires and found that it was 32 psi at 18 degrees Celsius.
Wow,
So there is P1 and T1, 32 psi. Temperature is
18 degrees Celsius, or
not or,
no,
definitely the other.
definitely the other.
Okay. What is the correct temperature? 291. Must be in Kelvin. Okay, after 2 hours of driving, she found that the pressure had increased. Now, in theory here, let's talk theory. Why would driving a car increase the pressure inside your tires?
Sorry.
Yeah, friction makes your car tires heat up, which is going to heat your gas particles inside, therefore making the pressure go up because the volume of your tires is probably going to change in time. Yeah.
That's about like when people fill up their tires in the winter, they go and they fill up their tires all the way.
Too
I'm
much,
like,
yeah.
and I'm like, you're dumb because when it warms up, you're gonna.
Clearly, yeah. Yep. All right, and then your T2. I want to show you how to solve this guy because, believe it or not, a lot of even sophomores and juniors still struggle with solving a variable on bottom. So,
Why can't you just solve it like this?
you absolutely can. Okay, good. That's what I'm doing. What am I doing? That's wrong. P1 over T1, P2 over T2. Now stop and listen. You're solving for this variable. I don't know if you guys went through math class not knowing this, but there are two things that have to be true when solving for a variable. The first one is,
Has to be alone.
it has to be alone. Second one is,
It has to be.
on top of a fraction. Because here's what ends up happening. People go like this. They go, oh, I'm going to divide by P2. And then they're like, voila. What did you just do?
1 over 2. Yeah.
A lot of people get rid of the fraction and they miraculously move it to the top of the fraction without doing anything to get it there. Okay? So there's quite a few ways that you could solve this particular problem. Okay? You could use the cross multiplication method. You guys familiar with that?
I think so.
This times this equals this times this. That's going to bring it to the top. Another method, the reciprocal method. You ever heard of that? What do you do with the reciprocal
You
method?
flip this.
Take the reciprocal. That would flip it. Well, that would flip both. Would that get T2 on top?
Yep.
And you could just multiply by T2 and bring it over here. There's 3 ways you can do it. Whatever you feel is the easiest. I find that just taking the reciprocal is the easiest. It's up to you. You can do what you want. Then you would multiply by P2. Your answer when you do that should be 310 Kelvin. Now we didn't get to the last 3. The last 3 we're dealing with same type of thing, except for they were different gas laws. You should figure out which gas law to use.
Oh, you mean for this?
Yeah. Otherwise, nothing new.
Control is good little thing.
Can I be the best? I want to be sick just for this class.
So mad.
Right on camera. He got that.